Welcome to EDAIC Monitoring Physics, Part 2, produced by Critical Core Academy. In Part 1, we built the core monitors. In this lecture, we move closer to the anesthetic machine. Oxygen analyzers, anesthetic gas analyzers, flowmeters, pressure regulators, and the safety systems that stop a hypoxic mixture reaching the patient. Keep one exam principle in mind. The machine does not just deliver gases. It measures, regulates, protects, and sometimes fails. A strong EDAIC answer explains the physics, then explains the patient safety consequence. The full EDAIC preparation course is available at criticalcoreacademy.com. Let us map the lecture before we go deep. First, oxygen analysis. EDAIC questions often compare galvanic fuel cells with paramagnetic analyzers. You need the mechanism, calibration, response time, and failure modes. Second, anesthetic gas analysis. Most clinical analyzers use infrared absorption to measure carbon dioxide, nitrous oxide, and volatile agents. The exam likes Beer-Lambert law, sampling delay, water traps, and how the monitor identifies an agent. Third, the anesthetic machine. We will divide it into high-pressure, intermediate-pressure, and low-pressure systems. That simple map helps you place regulators, flow meters, fail-safe devices, hypoxic guards, and the common gas outlet. There are two oxygen analyzer principles worth knowing very well. The galvanic fuel cell is electrochemical. Oxygen diffuses through a membrane into an electrolyte. At the cathode, it is reduced, while a lead anode is oxidized. The chemical reaction generates a current, and that current is proportional to the partial pressure of oxygen in the sampled gas. Because the cell consumes reactants, its output gradually falls with age. Paramagnetic analysis uses a very different fact. Oxygen has two unpaired electrons and is weakly attracted into a magnetic field. Most anesthetic gases are diamagnetic. In older designs, oxygen displaces a nitrogen-filled dumbbell. In newer designs, a pressure difference or thermomagnetic flow is detected. The key exam phrase is, the signal is proportional to oxygen partial pressure, and the response is fast. Calibration is not a decorative step. Oxygen analyzers measure oxygen partial pressure, but the display is a percentage. Changes in pressure, water vapor, sample site, and calibration can therefore affect interpretation. A galvanic cell is simple and self-powered, but it is slow compared with the paramagnetic systems, and its output falls as the cell is consumed. If the cell is exhausted, contaminated, or poorly calibrated, it may read falsely low or fail to respond. A paramagnetic analyzer is fast enough for breath-by-breath inspired and expired oxygen, but it needs good sampling conditions. Water, blocked sample lines, incorrect flow, leaks, or pressure changes can create errors. In the exam, always connect the failure mode to an action. Increase oxygen, check the circuit and source. Use the backup cylinder if supply is uncertain, and verify with the independent oxygen analyzer. Now move to the anesthetic gas analyzer. Infrared spectroscopy works because molecules with dissimilar atoms absorb infrared radiation at characteristic wavelengths. Carbon dioxide absorbs strongly around 4.3 micrometers. Nitrous oxide and volatile agents absorb in other infrared bands. The analyzer sends infrared light through a gas sample and measures how much light reaches the detector. The Beer-Lambert idea is enough for most EDAIC answers. Absorbance increases with concentration and path length. In clinical monitors, The mathematics is corrected for pressure, temperature, overlap between gases, and instrument calibration. But the core physics remains simple. Each gas leaves a fingerprint in the infrared spectrum. Modern multigas analyzers do more than draw a capnogram. They measure inspired and expired carbon dioxide, nitrous oxide, oxygen, when an oxygen sensor is included, and volatile agents such as sevoflurane, desflurane, isoflurane, halothane, and influrane. Agent identification comes from looking at more than one infrared band. A single wavelength may be misleading because absorption spectra overlap. By sampling several bands, the analyzer can compare the pattern with stored fingerprints and identify the primary agent, or warn about a mixed agent. The Mach number is not directly measured by a magic Mach sensor. It is calculated from measured end-tidal volatile concentration, sometimes combined with nitrous oxide and age-adjusted reference values. So, if sampling is wrong, agent concentration and Mach display can be wrong as well. A gas analyzer is only as good as the sample reaching it. In mainstream analysis, the measuring chamber sits at the airway. The signal has little transport delay, and gas is not removed from the circuit. But the airway sensor is bulkier. In Sidestream analysis, a pump draws gas through a narrow sample line to the analyzer. This makes the airway adapter lighter, but creates delay. The longer and narrower the sample line, and the lower the sampling flow, the greater the transport time. Water, secretions, kinking, leaks, or a loose sampling connection can reduce waveform amplitude or create falsely low concentrations. For EDAIC, do not just say sampling delay. Say what it changes. The displayed event lags behind the airway event, and rapid respiratory changes can be smeared or missed. The anesthetic machine becomes much easier if you divide it by pressure. The high-pressure system begins at the cylinders. Oxygen cylinders may be around 2,000 psi when full, so the machine needs yokes, check valves, pressure gauges, and a first-stage regulator. The intermediate pressure system includes pipeline inlet pressure, usually around 45 to 60 psi. Second-stage regulators, oxygen pressure alarms, fail-safe valves, oxygen flush, and the flow control valves. The low-pressure system begins downstream of the flow control valves. It includes flowmeters, vaporizers, the mixing chamber, and the common gas outlet. This is the most leak-prone region because pressure is low, and small leaks may change the final gas mixture. In the exam, always ask, is the problem upstream supply, pressure regulation, or final gas delivery? A mechanical flow meter, or rotameter, is a variable orifice device. The tube is tapered, narrow at the bottom and wider at the top. Gas enters from below and lifts the bobbin or float. The float rises until the upward forces from gas drag and buoyancy equal its weight. At that height, the annular space around the float corresponds to a calibrated flow. The tube must be vertical, the float must spin freely, and each tube is gas-specific. At low flows, flow may be more laminar and viscosity-dependent. At higher flows, turbulence makes density more important. This is why you should not interchange tubes or floats between gases. The oxygen flow meter is positioned downstream. So if an upstream nitrous oxide or airflow meter leaks, oxygen is still added last before the final mixture leaves the flow meter bank. Gas supply questions are really pressure physics plus safety. Pipeline oxygen usually reaches the anesthetic machine at about 45 to 60 psi. A full oxygen E-cylinder has much higher pressure, so the regulator reduces that pressure to a stable working range. Oxygen behaves as a compressed gas. Cylinder pressure falls progressively as oxygen is used. Nitrous oxide is different because it is stored partly as liquid. Its pressure may remain near the vapor pressure while liquid remains, then fall rapidly once only gas is left. That is why pressure gauges estimate contents differently for oxygen and nitrous oxide. Safety indexing helps prevent wrong connections, but it is not enough. A crossed pipeline can still deliver the wrong gas at the right pressure. The independent inspired oxygen analyzer is the final protection against that specific disaster. Hypoxia prevention is layered, and this is a common EDAIC trap. Pin index and diameter index systems reduce the chance of wrong gas connection. Regulators stabilize pressure. Oxygen pressure alarms warn when oxygen supply pressure falls. Oxygen failure protection devices, sometimes called fail-safe valves, reduce or stop nitrous oxide flow when oxygen pressure is too low. But notice the limitation. A pressure-based fail-safe device responds to oxygen pressure in the oxygen line. It does not chemically prove that the gas is oxygen. If the oxygen pipeline is connected to the wrong gas at adequate pressure, the fail-safe may be satisfied while the patient receives a hypoxic mixture. The hypoxic guard or proportioning system links oxygen and nitrous oxide flow settings to reduce the chance of dialing a hypoxic mixture. The independent oxygen analyzer remains essential because it measures the final inspired oxygen concentration. Here is a practical exam framework. For any equipment physics station, start with the physical principle. Is it magnetism, electrochemistry, infrared absorption, pressure reduction, or flow through a variable orifice? Then describe the signal path. Where is the sample taken? What reaches the sensor? How is it converted into an electrical signal and displayed? Next, mention calibration and dynamic behavior. Is there a 0 point, a span point, a response time, or a sampling delay? Finally, name failure modes and a safety action. For oxygen analyzers, think exhausted cell, poor calibration, sample leak, or water. For gas analyzers, think blocked sample line, water trap, overlap, or delay. For the machine, think pipeline failure, regulator failure, low pressure leak, wrong gas, or hypoxic mixture. This structure turns physics into a safe clinical answer. Let us finish with the high-yield memory. A galvanic oxygen cell generates current from an oxygen-consuming chemical reaction. A paramagnetic analyzer uses oxygen attraction into a magnetic field and responds quickly. Infrared gas analysis measures molecular fingerprints. It can quantify carbon dioxide, nitrous oxide, and volatile agents, identify the agent, and calculate a MAC display from measured concentrations. But sampling delay, water, leaks, and line obstruction can make the display misleading. The anesthetic machine protects the patient through layers: correct connectors, regulators, pressure alarms, oxygen failure protection, hypoxic guard, and final inspired oxygen monitoring. This lecture is part of the EDAIC preparation series by Critical Core Academy. For the full structured course, notes, tests, flashcards, and audio learning, visit criticalcoreacademy.com.